So, good morning, everyone. You've had a whole bunch of computing kind of pushed down your throat. A lot to think about. I don't really do computing anymore. I kind of gave that up about 20 years ago. But I'm going to teach you about the next generation of computing. Get you a start on it. It's actually built on the foundation of electronic computers. And I think you're going to find that this is, it's going to be more accessible to you than you might think. It's programming living things. Now, I'm a genomic scientist, which means really I think about genetic-y stuff all day long. I'm kind of one of the original bio-geeks. This is me at work. It was snapped just by accident. You can see I've got a coffee cup. I've got a glass of wine. I like to keep things balanced. Got a book on corporate strategy. It's an easy life. I work with a company called Autodesk. Many of you have probably heard of it because it makes software, design software. This building was probably designed in Autodesk software. And I got my job with Autodesk by asking them a question. You build design tools for everything, I said. But do you want to design living things too? And they said, yeah, that would be totally cool. So I've been working with them for the last 2 years. They've been exploring the space for the last 4 years. And our whole goal right now is, can we actually make tools that make it easier to build living things, to build things from the nanoscale, to build self-assembling matter, which is a completely new class of materials. I think about evolution all the time. It's just something I do. We've heard a little bit about space. Stars really unlocked the universe for us, right? Like, we've always known the stars were there. It inspired us to build things like rockets. This is Goddard back in the 1920s. Ultimately, the space shuttle, now retired. Now we're moving into private industry, which is absolutely incredible with things like the Dragon capsule. And you just saw that today, basically anyone that wants to go to space can, which is a remarkable evolution in technology, in abilities, and capabilities. And that's not going to stop. Already, there's designs to get to Mars and actually set up a base. And DARPA is exploring, can you build a spaceship that's good for 100 years that will actually allow humanity to go out and seed? So evolution is an ongoing process. We just happen to be here in it today. Of course, computers went through a rapid evolution too. We know this, from big room-sized machines to ultimately personal computing, the starts, the homebrew, the professionals getting into it from other things. Of course, different groups coming into it on, starting to add their creativity, working out of garages, ultimately becoming toys. New people coming into the space since it got so big, ultimately realizing it's not just computers that want to connect, but us meat puppets too. And ultimately now, man, how many of you have like 2-year-olds that their favorite toy is the iPad? Like, everyone is online these days, and it's not stopping here either. Evolution seems to be one of the basic forces of the universe. And of course, life figured this out long ago. These are bacteria. These are cells of E. coli scanned in an electron micrograph. They don't look like too much. Their whole purpose in life is to grow and divide, grow and divide, grow and divide, consume resources, grow and divide. This is what I started studying almost 25 years ago. And they're beautiful little machines. Absolutely incredible. You never look at sausages the same way. Just ever. They are, we won't go there. But they are machines. And this doctor, David Goodsell, loves to show the complexity of these machines in these drawings that he does. And he kind of zooms in on some of the machinery, and here you see some of the locomotion materials. They're called pili. It actually uses it for flagella. It's used as a whip to essentially allow it to swim. The other things are basically antennas. You start looking into the molecular components of this system. It's all different proteins. There's over 4,000 different proteins, all working together, components to build these systems. And what you're seeing here is actually the clutch of the flagella, the motor that actually drives this thing along. And it really is a molecular motor. This thing will spin. And it's not static. Every single protein in a bacterium is in constant Brownian motion. It's just the heat energy that provides all of the mechanical force necessary for life to come together, for it to operate. And every molecule in a bacteria will bounce into every other molecule in a very short period of time. These days, I don't end up talking so much to biologists. They look at this stuff and they go, yeah, I studied all this ages ago. I end up speaking to people like you that work in computers. Because what we're learning now is that the architectures we've been building in computers for decades actually are really similar to the architectures evolved by pretty much all living things. Basic circuits, individual components, more complex modules, the computer itself. In fact, bacteria, really are little computers. And when you string them together, you actually get networks. And today we live in a world of networks. But I like to point out that we are essentially networks. We have 100 trillion living computers working together in a cohesive way to build a network that you get up out of the morning and drag to a conference. It's really remarkable. We haven't done anything like this yet in electronic computing. We have so much to learn, but there's a lot of cross-fertilization. And more than that, this is how you make new computers in a biological world. They just do it. This is a time lapse, but about every 15 minutes, an E. coli bacterium can divide. So you start off with one bacterium, and you end up with billions in 24 hours. In fact, they're kind of little MakerBots. I love this part about bacteria. If you step on a bacteria, in this case it was squished in a glass slide, its genome comes out of it. That's its genome. 4.5 megabits of DNA. Not very much. This is a classic photo. And when I saw it the first time, I just saw this. And now you get it. That's all the genomics knowledge you need to know. Literally, DNA is just the magnetic tape of a living organism, and it's a digital code. In fact, what we're really starting and seeing now, what we've been building ever since we started sequencing genomes, is really creating a whole new field of biology, digital biology. And it's fascinating. And when you do it with DNA, it's the only thing that you can absolutely know for certain about a living organism, because most of the living things are analog. But, DNA is very discrete. It is digital. Today, you can read DNA easily. 20 years ago, it was hard. Now you can just go buy one of these devices. They cost about $150,000. You plunk them on your desk like they were a laser printer. You learn a few protocols, and this thing will churn out a couple of human genomes a day. At the heart of this is a little chip that all the reactions happen and are immediately electronically recorded and uploaded. It's a beautiful device. It's a 4th generation sequencer. This is the 5th generation. It's produced by a company called Oxford Nanopore. It's raised over $120 million in investment funding. And it is essentially no moving parts. It basically, DNA winds its way through a little hole called a nanopore. And as the DNA molecule goes through, it's like, people going through a doorway, you can actually measure the difference, the electrical differences of the molecule going through that hole, and read directly the electrical signatures. This will sequence a human genome. Apparently, it's not released to the public yet, but they say it'll do it in minutes. Moore's law we all know in computing. About every 18 months, price performance essentially doubles in computing. It's a nice straight line. It's been a straight line pretty much, and this line is predictable. The whole industry runs on it. genome sequencing was tracking that pretty closely. And then something happened in 2007, 2008, and a new generation of sequencers came in, and it's blown those cost curves away, up to 500% faster. I've never seen any technology on the planet advance so quickly as the reading of DNA. In 2000, as you know, after 10 years of international development, the first human genome was read. All in the cost, it's hard to get a straight number out of this because it was so big, but it was somewhere between $3 and $5 billion worth of effort to read that first human genome. That's a lot of money. A couple of months ago, I flew up to Toronto. That's my arm and a Band-Aid. I gave a little bit of blood, and I got my genome sequenced and interpreted for $4,000 bucks. Most of the money was for interpretation. About 1,000 of it was for the actual DNA sequencing. We don't even know what to do with this data yet, because my genome sequence is the whole barcode for me. And right now, they told me I was the 10th Canadian to get this done. Because I'm, yes, Canadian. But there's been a few thousand Americans done, and globally, we're in the tens of thousands now. But it's going to change really rapidly if you understand that cost curve. We're all moving into comprehension. That's the hard part. That's where the big computing comes in right now, besides just storage. This, if anyone's ever taken a biochemistry course, they've seen this before. This is essentially, badly in low resolution, this is essentially the metabolic circuit for a single cell. If you zoom in, it gets more complex. This was the work of thousands of biochemists for decades. And it kind of sucks. Doesn't really tell you all that much. It's just a big circuit diagram. This was published a year ago, and it's actually the world's most advanced simulator of a living organism. It encompassed hundreds of different experiments, kind of put it all together into an interface, and you can kind of watch a cell grow and divide and all the protein expression, etc. Again, boring. This is not going to inspire anyone to go into life science. But it's writing DNA that gets really fun. Genetic engineering. Ooh. Ooh. We've been doing it for 40 years, but we used to do it with recombinant DNA technologies. You've all heard it, cutting and splicing. It's literally using preformed DNA and scissors, molecular scissors and molecular glue to stitch together new code. And it's kind of ransom note style, right? It takes a long time. Imagine if you had to write all the code you do this way. Imagine if you couldn't actually see what you were doing because it's nanoscale. Imagine if you had to go into a facility like this to write a line of code. It's hard work. That's why I took a PhD to become a genetic scientist. Not anymore. About 10 years ago, companies like this started to pop up. DNA 2.0. In fact, it just celebrated its 10th anniversary. This business exists to compile genomic data. You send them a file of genetic code, they'll print it. That means if you can type, you can be a genetic engineer today, which is pretty amazing. It's given rise to a whole new community of programmers that I've had the privilege to be able to work with. These are a couple of guys in Cambridge, England. What they wanted to do was make bacteria glow as bright as they could. So they built all these different glowing bacteria in all different colors. This is at MIT last year. The world's elites of the students coming through an international program where their whole mission is to program the coolest thing. It's now an international program. 16,000 students have been through this in the last 10 years. They design their own projects. They do it in 3 or 4 months of summer work. And they have a giant conference. And they show off what they've done. There's competitions, there's prizes. And ultimately, at the end of all of this, one team gets to go home with this BioBrick trophy. It's like the Stanley Cup of genetic engineering. And it's an honor to be on it. And I think basically everyone that has is pretty much under 25. But that wasn't enough. It was only this iGEM program that I just showed you from MIT was only running for a few years, and people said, I don't want to do this just in the summer for a competition. I want to do this all the time. So they started an organization called DIY Bio, do-it-yourself biology, very much like the Homebrew Computing Club, except really with more homebrews. They started setting up labs in garages. This was a cancer lab set up in a garage in Sunnyvale. Now they started to set up community labs. This one's in Brooklyn. There's others popping up all over the world now, even in bedrooms. This is Cathal Garvey. He's Irish. He set up a licensed biotech company in his mom's spare bedroom. Like this is just like when you used to sit down in the basement playing with the computers. And now there's kits you can buy that basically have everything in a box. Take it home, learn how to do some of this stuff. It's targeting high school students and preschool. Not preschool, grade school. I guarantee you've all done some genetic engineering, just maybe not in maybe in your master bedroom. You know what I'm talking about. We're starting to see the rise of a whole new biotech industry. The students that were actually teaching this program at MIT when they graduated, they set up a company called Gingo Bioworks. They just bought a whole bunch of robots on eBay that were really cheap, and because they were broken, they fixed them. Hey, they're MIT engineers. Got them up and running and started building contract microbes. They're not afraid to tell the world, we build microbes. Come. This isn't the same genetic engineering that you hear about in the newspapers. This is genetic engineering that's done for creative reasons, for powerful reasons, for industrial reasons, for just because you want to. And it's global again. This was a friend of mine in China, part of a new group out of one of the largest sequencing centers that's also now learning how to write DNA. We're seeing companies like this, Synthetic Genomics, pop up. It's their whole job, write synthetic genomes. Genomes, just think operating systems. That's it. That's what they are. These guys, all they do is make synthetic operating systems. And this company just went public a few months ago in Trexon. It's been kind of quiet, working in the background, doing metabolic engineering, essentially manipulating operating systems. And they're worth something like $2.5 billion right now. A tiny company in the space, but one to watch. But I like to bring this down to a level that everyone can understand. Beer. Because you're not going to get interested in something unless you can relate to it. Beer is one of the most highly consumed beverages on the planet. This is how you make beer. You need some of these little guys. This is yeast. You all know yeast. You go to Safeway, you open it, you buy Fleischmann's yeast. You go inside, it's a little powder, right? That's actually a freeze-dried living organism. All the water has been taken out of it, which is kind of like taking all the electrolyte out of a battery. It's dead. Doesn't work. But all the bits and pieces are there, and when you add a bit of water to that yeast, it boots up. That allows you how to, and it loves to eat sugar, and it loves to make carbon dioxide, which is why your bread rises. And it also can produce ethanol, which we love as human beings. Beer. Yeast engineering has gone so fast. Lots of people work with bacteria, but bacteria scare people. Yeast, for some reason, doesn't. We've been working with it for 10,000 years. You can find documentaries that basically assert that civilization started because of beer. And frankly, I kind of believe it. These were my favorite students from MIT last year. They actually were they came to MIT, they were from Munich, Germany, where they know their beers. Like they really know it. And they engineered 4 beers over a 4-month program in the summer, and they brought it to MIT. One was a cancer-fighting beer. Just get that aside. You need to fight cancer. They made a beer with a different flavor, lemon flavor, all produced by genes they'd introduced into the yeast. They made a sweet beer by adding a protein-based sweetener to the yeast. That was kind of cool. But what I really loved was that they took the entire biosynthetic pathway from coffee that makes caffeine and they dropped it in yeast. Caffeinated beer. If anything deserves a Nobel Prize, I don't know whether to fall asleep or stay awake. But anyways, now this is actually really serious science. Because now scientists have said, we're going to go and make a completely synthetic yeast. We made a completely synthetic bacterial genome 3 years ago. It got headlines for a day and then everyone forgot about it. But now they're working on this synthetic yeast. There's a whole Yeast 2.0 project with millions of dollars in funding going to it. It's an international project to boot up a synthetic yeast. And trust me, it's not going to be just for ethanol anymore. People are already hacking yeast for biofuels, for specialty chemicals, for all sorts of flavorings, for all sorts of different things, and you can bet more than one intoxicant is going to be added. I also like to talk about glow. We all love things that glow. We're humans. We just, glowy, shiny things. It works for us. As scientists, we've been making glowy stuff for a long time. Glowy mice. Glowy bacteria, I won't even go into because that's really kid stuff today. Glowy cats. I would love a glow-in-the-dark cat. I've tried to buy them. There's no one selling them yet. But I would love a glow-in-the-dark cat. You could find where it is in the neighbor's bushes at night. Hey, back here. Is there a sensor for that yet? Beep, beep, beep. Glow-in-the-dark monkeys. We're only one step away from glow-in-the-dark humans. You know that. But we're not going there. Instead, glow-in-the-dark plants. Some people that saw me give a talk on this a number of years ago said, we want to make glow-in-the-dark plants. Trees that glow brightly at night to replace streetlights. And so they ran a Kickstarter, the first ever in synthetic biology, and they got 8,400 backers that said, yeah, we'll help you make a glow-in-the-dark plant. Now, it's a completely useless plant. And just to warn you, it's useless. It's ornamental. It's not going to grow into a giant tree in your backyard. But the fact that the technology has gotten to the point where a group of young scientists can get together, crowdfund a project for almost $500,000, and seriously do this work, because it's not hard science, is amazing. It's a testament to how far genetic engineering has come. Meat. Meat's important. We went out for barbecue here last night, and you do it right here, I gotta say. But this is how we do meat in the lab. We have 3D printers that print cells to produce meat. It's still way too expensive. You can't go make a big giant porterhouse right now. So people are making little tiny slices of liver. This is a synthetic liver, three-dimensional tissues. It behaves very much like a human liver, and they can make tons of it, all in little tiny discrete wells. So this company, it's called Organovo, it's based out of San Diego, makes synthetic liver for pharmaceutical companies to go and test their drugs on, so that we don't have to hurt some animal's liver or your liver. It allows them to do drug screening so much faster. But this is just the tip of the iceberg when it comes to printing meat. Because we all need meat. Our meat gets old. We have such a long waiting list for replacement organs now, it's stupid. It's 10 times the supply we have available now, and most people aren't getting put on the list. So one day we're going to crack the ability to go and make other pieces of meat that we need. And then this group, Modern Meadow, is already taking the technology for 3D printed meats, which is coming down in price really fast, and starting to make 3D printed leathers. And they really want to go and make 3D printed meat you can eat. I don't think it's going to compete with cows anytime soon, but they point out, look, when you take in the total cost of producing animals for meat, the amount of water, the amount of land use, all the pesticides, fertilizers, et cetera, the conversion rates of energy, eventually this wins. Eventually this wins, and they know it. And the first meat burger using this technology was cooked this summer in kind of a promotional event. The tasters said it was not horrible. You should have seen the prototypes. It cost about $100,000 for this burger, though, so I don't think it's going to be on McDonald's anytime soon. But, you know, exponential technologies, they get cheaper. And already the bioprinting technologies are getting, you know, so fast. People are hacking old printers and already 3D printing glow-in-the-dark bacteria at some of the hacker spaces. I love BioCurious, this hacker space in the Bay Area. And those are glowing bacteria printed on a plate using a homemade 3D printer. Kind of cool. And we all need more robots. Robots, 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 robots. We're learning how to actually make nanoscale robots now using some of these genetic technologies. This is actually a genome that's been folded to produce different shapes. At the top is the computer model, then it's simulated, and then the lower layers are actually electron micrographs of a genome that's been folded based on these models. We can actually, this is only done in 2 dimensions, but you can see you can pretty much make any shape. And when you can turn DNA into happy faces, it really demystifies it a lot. It's not so scary. And in the years since that was invented in 2006, people have gone on, and this was published last year, this is a nanorobot designed specifically to hunt down cancer cells. It's actually made of DNA as a structural material because we know the thermodynamics of the DNA molecule really well. We know how to fold it. And it's kind of like a flip phone. When it's closed, it's completely inert. But it's got a little key at the end of it, and when it binds to a cancer cell, it flips open, and on the inside are these little cancer-killing proteins. And it goes, boop, kills the cell. Works perfectly in a Petri dish. It's not coming to a cancer hospital near you anytime soon, but this technology is all accessible using a laptop. It's all can be made using printers. So it's going to grow fast. In the intro, they said that I had a company, a co-op, in other words, an open source company, trying to make viral therapies for cancer. When I started this company a few years ago, it was just ludicrous. There was no way you could actually do this type of work for any type of cost basis that people would actually donate for. But in the years since, we've seen Kickstarters and Indiegogos raise millions of dollars for projects. And the technology is getting incredibly cheap. I like working with viruses. Now, viruses scare most people. But really, viruses are just the apps of the biological world. You know, our genomes, operating systems. Viruses, apps. They're some of the absolute best genetic engineers on the planet. This was the first synthetic virus that was published. Actually, I just learned the other day it was probably the second synthetic virus, because another group of scientists published a synthetic virus, but they didn't want to make a big deal, so they just kind of buried it in some footnotes. But this is a synthetic virus that was made in 2002, almost a decade ago. And it cost about $500,000 to make, and all to make a synthetic virus, it's actually pretty easy. You just take the genetic code, it's already published on the internet, you can trust it. And you print out the DNA, which, okay, today you just email the file. And then you drop that DNA into a permissive cell culture. Or you break all the cells open so all the guts of the cells are there. And essentially all the machinery of the cells will take that DNA and it'll make virus particles. It's even easier than compiling a new app for your Android phone. People are using viruses in so many different ways now, I'm losing count. This is a company created by a couple of grad students that just makes viruses to look for essentially bad bacteria in hospitals. Lowered the cost by a factor of 10. They raised $13 million, you know, basically before they finished their PhDs, and they're doing great. This company uses viruses to turn methane, essentially cow farts, into ethylene, which is essentially your plastic cups. You know, which is really, and you might laugh at that, but they've raised over $100 million, and you haven't. This guy I really like, Philip Dornmeister. He works for a company called Novartis. Novartis makes a lot of vaccines, essentially a lot of the world's vaccines. And you know, every year it's flu season, and every now and then you get a super flu that kind of scares the hell out of everyone. Well, he partnered with the company Synthetic Genomics, and they showed that they could take a new flu popping up. In this case, they test fluid on one that popped up in China earlier in the year. Popped up in China without receiving a sample of that virus. They had it sequenced in China, emailed the sequence over to Synthetic Genomics. Synthetic Genomics made a viral vaccine. They attached it to the backbone of a Novartis virus that they use for making all the different vaccines, and they had it up and running and growing in 3.5 days without ever having any isolate of the original virus. That's incredibly cool. This is the biggest upgrade to vaccine making in 40 years. So it's starting. But my favorite stuff is cancer, because cancer, just think of it as disk corruption. We all have disk corruption on our computers. You know, as Chris was saying, throw them away. That's what your body does most of the time. It throws away billions of cells every single day because it has some sort of a hardware fault or disk fault. But occasionally, you get a 1 in 100 trillion event, probably even higher odds than that, where that little cancer says, I'm not being deleted. And it takes root. It starts to grow a new network in your old network, and it starts to crash the system. That's all cancer is. It's one of the simplest problems. Bacteria get infected by these little viruses. There's a whole ecosystem between bacteria and viruses. This is viruses swarming on the outside of a bacterial cell, and if a single one of those genomes gets in, it's going to take over that entire cell and produce more virus particles. There's a whole ecosystem around this. It's absolutely beautiful. And these things look like hypodermic needles. In the cartoon, in the electronic micrograph, in the molecular visualizations that scientists like to do when you give them free, expensive software. This is one of those viruses binding to a cell. It actually binds to specific receptors. They're species specific. They're incredibly picky. And it actually drills a hole into the cell and injects its genome. Scientists over 25 years ago started to co-opt that same mechanism, the same idea that viruses can infect cancer cells, specifically because they're picky, and reprogram them to kill those cancer cells. It's a whole giant field. It's called Oncolytics. And companies like this one, Generics, are kind of at the forefront of it. All these companies have to raise hundreds of millions of dollars to advance a drug through clinical trials because it's so hard to do. But we're starting to see evidence that it works, even on a personalized basis. This is Emma Whitehead. She had a really, really nasty leukemia. Wasn't responding to any of the drugs. The researchers reprogrammed HIV, you know, something we're normally afraid of, to go and hunt down her cancer cells. And it works so brilliantly, she's basically cured today. We're all developing technologies. You guys making the computer stuff, other folks building the genomic stuff, to make that type of thing easy to do, cheap to do, fast to do. And we're right at the start of that now. And of course, it means we're going to have to completely change all the old school ways of doing security, just as we've had to completely rethink security in a cloud world, in a fully connected world, in a digital world. So all this stuff is changing. I like to play with these ideas. I like to see how far I can take them. Last year, with a writing partner, Mark Goodman, an expert in cybersecurity, we wrote a piece called Hacking the President's DNA and published it in the Atlantic magazine. That caught the president's attention. I didn't get invited for dinner. But they really said, no, it's about time we started thinking about this, because all the stuff you guys are learning about cybersecurity all applies. You can hack DNA as easily as you can hack electronic code. And in fact, we wrote another piece this year, just in Wired, kind of explaining some of the common hacks and some of the similarities. Spam. I can make that easy for you. Pollen. That's spam. Seeds, in general, spam. Sperm, spam. Because this is really new and because we're also unfamiliar with it, even though we are all made of living cells, of living things, of genomics, we're kind of blind to it. We take it for granted. We're in this weird period now. This kid, 20 years old in China, is running an international program to essentially read the genomes of 2,000 brilliant people, geniuses. He's trying to look for the genetic markers of genius, because he's a genius himself and he wants to find his friends. Maybe it's going to generate the next, down the road we'll have, a whole industry just churning out geniuses. I don't know. All I know is it's weird right now. It's unfamiliar. These two guys popped up on my radar last year because they want to do something called Genome Marketing. They want to read your genome, not just your genome, but also the genome of your microbes, and tell you or suggest to you, what toothpaste you should buy, what skin cream, what shampoo, who you should date. What about blue tomatoes? I just throw this in for fun. Maybe they should glow in the dark. I am still waiting, though, for someone to enzymatically catalyze carbon into another useful form and crash the diamond market. And if you think this couldn't happen, you're probably wrong. Nature has generated amazing enzymes that do some of the most wicked-ass biochemistry you could ever imagine. It's just there's no biological reason to make diamond. But there's already indications that nature can make things like carbon nanotubes. We're starting to learn how to look for that stuff now. Here's another weird one. There is a serious project underway now, serious discussion for de-extincting organisms, like woolly mammoth, like the passenger pigeon. There's no reason that any of you have to really go extinct, individually or as a species anymore. We can boot it up, back it up. Aging. I'm living this. I've got the distinguished title. But we're also starting to hack some of the mechanisms around aging. This was a New York Times article. The mouse on the right is the same age as the mouse on the left. It looks really healthy. All they had programmed into that mouse was a little switch that said, if any individual cell starts to get old, just have it commit suicide. There's still lots of growth in the organism to replace that cell. It's kind of like, knowing the mean time between failure of all your computers. Just throw away the old ones, slap in a new one. It didn't live any longer, but it looks like it lived a lot happier than the mouse on the left. And then, of course, you all saw the Time magazine. Can Google solve death? I don't know. But just the fact that a computer company is asking this, that's kind of wild, isn't it? Like, things are changing. And this guy, Dmitry Itskov, made a fortune in computers. Now he believes that he's going to be able to make androids, cyborgs, by 2045. There's a whole project on this, and he's absolutely serious. He's only in the second year towards this, but he had a conference with 600 people at the Lincoln Center in New York City with some really amazing scientists. So this is cool. But why care? Really, why care about any of this shit? You got jobs, you got computers, you're busy. Well, this is a graph of drug development for the last 60 years in terms of outputs. It's not one of those beautiful exponential growth curves you're used to seeing in computers. In fact, it's an exponential decrease in the number of outputs per $1 billion invested. The whole drug industry is failing. And if you want to make some money, don't hack computers, hack drugs. We've got a whole new set of tools for this. Or you probably read this week that in Harbin, China, you could only see the length of a football field because of the smog. That's partly because of the economies we've generated around our industrial world today, including the computers that suck so much power, et cetera, et cetera. Garbage. We are such a wasteful people. I won't even go into the landfill problems that are emerging around the world. We have lots of empty space here. Mexico City, not so much. 25 million people. Or the fact that we're overfishing our oceans to the point where we're already seeing massive stocks collapse, and more are coming. Like, this is global problems that we're not paying our attention to. I'm from Alberta, where we have oil sands, and this is what it looks like. Those little tiny things, bulldozers, right? Like, and there are hundreds and hundreds of acres of these types of oil sands, scooping oil up and spending massive amounts of energy just so we can wash it and fuel everything. But it was this picture from Chris Jordan, a photographer that went to Midway Island in 2009 and gave a great talk at PopTech that just made me, really, I just have to drill it into all of you. We have to do things differently. Midway Island is about as far from you and me as we can get. It's in the middle of nowhere. And he was photographing these albatrosses that had just basically died of plastic indigestion. You know, not retouched, hundreds of pictures, and you realize we got to change our ways moving forward. So I want everyone to kind of explore this field of genetic engineering. Compute Midwest, imagine the future. You know, like this, imagine the future. So I wanted to give you a little taste of how to go and do that. So I made my own little video inspired by the video you saw at the beginning. And here I am on a site called SGI DNA. It's a DNA translator. I'm actually writing Compute Midwest, imagine the future, and it's being translated into genetic code. This is really it's the ASCII compiler. I'm going to save the file. It's slow. I know I'm a slow typist. I should have sped this up. Should have read the instructions on how to speed it up. Boom, save the file. It's that simple. That's what genetic engineering has turned into. If you can type, you're a genetic engineer. And then you go into DNA 2.0, which will pop up in a sec. And all you have to do is upload that file, which is kind of cool. You go to a site like this. They essentially, it's pretty clean. It's not quite Google. You go into the account. You open a new sequence. You upload the file. Now, DNA is really just a string. It's like spaghetti. It's bits, chemical bits of information. It doesn't exist on its own. It can't amplify itself on its own. You have to put a little bit of a vector behind it. Essentially, you have to add it to another piece of DNA that will allow it to amplify inside the cell. So I've done that here. I've got my DNA loaded. I essentially choose the vector that I need for the backbone of this little piece of DNA. And I say, just splice this on. It doesn't take long. It is for me, blah, blah, blah. But once you have this backbone on this piece of DNA, you can put it into a microbe, and it becomes part of that microbe's operating system. It's like building a little app. And you find whether that microbe has the app or not by growing it on a little bit of antibiotic, because that backbone carries a gene for antibiotic resistance. And once you're done, you say thank you, and you hit the button, and you pay the price. And a few days later, actually instantly when you hit the button, it goes to a machine like this. This is an older DNA synthesizer, but it's the exact one that the company DNA 2.0 uses. It's actually been running since the 1990s. And then it goes into robots for assembling that DNA. And it goes through all these liquid handling systems, and ultimately robots like this to go and assemble all the bits into the right order. And then it shows up a few days later. It took me 4 days for them to get the order to me in a FedEx envelope. And it comes out in this little package like this. Inside the package, there's a couple of tubes, just in plastic, but written in DNA is Compute Midwest, imagine the future. Drop this into a microbe, it will live damn near forever. This message carrying forward. Just imagine what you can go and write. Really, there's going to be millions of people starting to write this code over the next few years. This century, we're going to rewrite the genomes of basically everything on the planet. It's one of the most remarkable times, kind of like being back at the beginning of computing. And we get to taste it. I've got a whole list of books. Anyone that wants to ask about this stuff is welcome to contact me. These are just some of the ones that I read that really kind of impressed me. And there's always more being added. And I just want to thank you for your attention and thank Autodesk for supporting me and Compute Midwest, Shutterstock.